We're going to turn our attention now to algorithms to produce certain types of circuits. So we're going to here do the nearest neighbor algorithm. This is an algorithm that we can follow to find a Hamiltonian circuit. And what we're doing here is specifically looking at a graph that has weighted edges, and we're looking for the Hamiltonian circuit that has the least amount of weight, okay, the shortest path or shortest circuit that visits every vertex. So the nearest neighbor algorithm, abbreviated as NNA, this is an algorithm that is what we call efficient. And an efficient algorithm is one that takes a reasonable amount of time. A reasonable amount of time. Okay. Some algorithms, though they are great at getting the perfect solution, they actually take too long. And we mean too long even for computers to do. Okay. So what we're doing is looking for algorithms that we'd be able to put into a computer to have the computer run. But we don't want the computer to crash because it takes too much computing power. So an efficient algorithm is one that actually works pretty well. The nearest neighbor algorithm is not optimal. Okay, not optimal, meaning it may not actually give us the best circuit with the actual smallest weight, edge weight, but it still produces something that's approximately correct. We're in the search for optimal algorithms generally, but we're going to start off with this one, which is not optimal. It's not always going to give the best answer. So the nearest neighbor algorithm is just, we're going to start with a vertex, and it doesn't matter which one we start with. We're just going to pick one to start with. I'm just going to start here with vertex C. Oh, sorry, beginning with vertex A. Let's start with A. So here's vertex A, and then we write A. And the nearest neighbor algorithm says, from A, just pick the edge connection that has the smallest weight, which in this case is the connection from A to D. All right, so I'm going to go from A to D. Okay, and that connection has a weight of 1. I'm going to write a 1 above that. Okay, then from D, we take the next edge that has the smallest weight. We can't backtrack. So we've got 8 or 9, and of course 8 is smaller, so we're going to use that edge there to go to C. And the connection from D to C has a weight of 8. All right, from C, we can't go down to A because we need to we can only visit unvisited vertices until we've visited all of them. So I haven't visited B yet, so I have to go that direction. I have to come down to B. And from C to B, that is a weight of 13. But now I've visited every vertex. So once you've visited every vertex, you connect back from where you ended to your starting point. Okay, so we went back to A, which has a weight of 4. All right, now to get the actual weight of this circuit, this Hamiltonian circuit, we just add these together. So 1 plus 8 is 9, 9 plus 13 is 22, and 22 plus 4 is 26. So we found a Hamiltonian circuit of weight 26. Now, that does not necessarily mean that that was the smallest circuit, okay? There is a better one, actually. But the nearest neighbor algorithm does not produce the optimal circuit. Here is an example of how a graph might be depicted. It may not be a picture, but it may be a list of our vertices in column and row, and then the numbers inside indicate the weight of the edge connecting them. So this table shows the time in milliseconds it takes to send a packet of data between computers on a network. So we've got computers A, B, C, D, E, and F. And we've got these times that it takes to send data between two computers. If data needed to be sent in sequence to each computer and then notification needed to come back to the original computer, we would be solving the traveling salesman problem, right? Where you start at one vertex, you need to visit every other vertex, but you don't want to repeat and then come back to where you started. So we are solving the TSP here. We'd like to find the circuit generated by the nearest neighbor algorithm starting at vertex B. So we start with vertex B. To apply the nearest neighbor algorithm, we now just need to find the connection from B that's the smallest. Okay, so I'm going to look along row B, and I see 44, 31, 43, 24, and 50. So the smallest one there is this 24 right here. And that's the connection to E. So I'm going to go from B to E, and that's a weight of 24 milliseconds from B to E. Okay, now because I visited E, I'm going to cross off that column so that I remember in the future that I'm not allowed to come back to E. Now from E, I'm going to go to my E row, and I see my connections, 40, 24, 39, 11, and 42. I cannot use B. I can't go back to B, okay? And so if you'd like, you can go ahead and cross off that column as well, because we can't go back to B until we've visited everything. So in E, the smallest connection there is to D, which is 11. So to D, 11, and I go ahead and cross off that column as well. That connection was 11, and now I'm in D. And in row D, I look for my smallest number. I see 12, 20, and 17. The smallest number there is the 12, which is to computer A. So I'm going to A, which had a weight of 12, and I cross off column A so that I know I can't go back there. Okay, now I'm at A, and so in row A, I see two connections left. I've got 34 and 41. The smallest one there is 34, so that goes to computer C with a weight of 34. I cross off C. Okay, now I'm in C, and I have to finish off my circuit. I have to visit what I haven't visited, so I've got this option here of 27, which goes to computer F. 27. All right, now I've visited every computer, but of course, because it's a circuit, I need to go back from F to my starting of B. So from F to B, now I just look from F to B is actually this connection right there, F50. Okay, so this circuit here is the circuit that's produced by the nearest neighbor algorithm, starting at vertex B. Okay, and if we were asked for the weight of that circuit, we would just need to add these numbers together. Okay, we're not asked for that in this problem, so I'm not going to worry about actually adding those. Okay, go ahead and pause the video and see if you can apply the nearest neighbor algorithm, starting with vertex E right here, and see what circuit you get. All right, we are starting with E. And from E, we pick the edge that has the smallest weight, and that is from E up here to B. That edge has a weight of 3, and so I go from E to B. I'll go ahead and put my weight there of 3 over that connection. Now from B, I need to use my smallest connection that visit something I haven't visited yet. So I've got 2, 9, and 5 as those connections, and 2 is the smallest. So I come down to connect to A with a weight of 2. All right, now from A, I can't go back to E, I can't go back to B. I take my smallest connection, which is from A to C, which has a connection weight of 1. Okay, now from C, there's actually only one thing I can even go to. I don't even need to look at anything else. There's only one vertex I haven't visited, which is D, so that's where I have to go. So from C, I go down to D. That has a connection edge weight of 2. And now that I visited every vertex, I just need to close my circuit. From D, I need to go back to where I started, which is at E. And that had a weight of 8. I can add those to get the total weight of the circuit if I'd like, and that gives us a weight of 16.